vector products cross product. You remember last night we discussed scalar products, some of the advantages or some of the physical interpretation of scalar products and how that is done mathematically and geometrically. What does it mean in a physical world? And today we are going to discuss about the other kind of multiplication that is used in mathematical physics for vectors, that is called the vector product or the cross product. As the name suggests, vector product means its output is a vector quantity, unlike the scalar product where the output was a scalar. So let's start from the same book that we were using during our previous classes, and I've already told the details of this book in our previous videos. I'll strongly recommend each one of you to go through my previous videos where I have started mathematical physics with a very layman languages, and probably each one of you will be able to understand what I'm teaching, and probably it will help you a lot. I'm keeping all the classes very short because I don't want you to learn too much in a day and then forget everything what has been learned in the following day. So it's good to grab bits by bits and understand the stuff fundamentally. So today in our class we'll discuss the vector product. As you can see here, I have the same book with me as the book by Tai Chow on mathematical physics, and we are on the page number 22. Here we'll be discussing the vector or cross product, or it's sometimes referred as outer product. It's not very common way to discuss a scalar vector product like outer product, but sometimes it is referred as outer product. So first it will be easier for us to understand what a vector product means physically, and then we'll probably go to the mathematical derivation of it, and we'll see some of the rules. So here, as the book says, let us say there are two vectors A and B, and we are trying to find out the cross product of A and B. Cross product has a symbol like cross, and you might remember the scalar product or dot product had a symbol of a dot here between two vectors. So let us say these two vectors multiply to give another vector C. Remember, the output will be a vector quantity. So now how to explain C, what C will be, what will be the numerical value of C, and since it is a vector quantity, what will be its direction. So let's go to a figure here. It's a very nicely drawn figure. You can see here. Let us say I have a vector A and a vector B. And as you can see here, if you put your right hand, like right hand three fingers, the thumb, the middle finger and the forefinger, in this way, the forefinger, if the forefinger is directed towards the first vector and the middle finger is directed towards the second vector, then the thumb will give you a direction which is the vector which comes out because of the multiplication or cross product of these two vectors. So you see here the angle between these two vectors is theta. So if you consider these two vectors as the sides of a parallelopipe, a parallelogram in 2D. You remember parallelogram with this side is equal to this side, and this side is equal to this side, and hence this angle and this angle is theta, and this angle and this angle will be 180 minus theta. So this is a parallelogram. Had it been 90 degree, it would have been a rectangle. And if you explode it in a three-dimensional geometry, it will be a parallelopipe. So what A cross B does is, if you represent A and B as the two consecutive sides of a parallelogram, the product will give you the third side of the parallelogram. That is about the direction of the product of A and B. If you extrude this area towards this axis, top axis, this will be the third side of the parallelogram. So you'll have the third side of the parallelogram in the cross product, and its length, or what we say as magnitude, will be equal to the area of A and B. Since we are multiplying A and B in simple 2D geometry, we know that if you multiply two sides of a parallelogram, it will give you the area, had it been a rectangle, of this parallelogram. So this C has magnitude that is equal to the area of this parallelogram, and it has a direction which is towards the third axis. And same way, if you try to reverse it, if you try to multiply B with A, means B cross A. So if you are doing it that way, you will have a product like this. Means you are starting from B and you are going towards A. So this finger will be actually here, and the thumb will go down, because there is no way you can put your forefinger beyond your middle finger and thumb still going up. So at that time, this vector will be basically in this direction. It will be minus of C. You remember, minus means 180 degree a scalar quantity, which is cos theta, is added to that, and that is why a minus sign comes. So when you are changing the direction of a vector quantity, means if you are multiplying A to B and you are trying to compare it with the multiplication of B to A, then you will get additional minus sign. So that will tell you the direction of the multiplication of A and B. So let's go back to what we were seeing. As shown in figure 8, if two vectors are form the two sides of the parallelogram, then C will define the side perpendicular to the parallelogram, and mathematically you can write it like this little thing here. The third vector C, which is equal to A cross B, we read it like cross, not the multiplication sign that we use in algebra, is the cross product, since these two are vectors. There is no sign on top of A and B because they are bold faced here in the book, and since these are italic, it means they are the magnitude of vector A and B. So the cross product of A and B, which gives rise to another vector called C, can be mathematically represented as the magnitude of A multiplied by magnitude of B sine theta, where theta is the angle between A and B, and a unit vector towards the direction of C. This unit vector is basically the vector which is responsible for the direction of the output vector. And remember, here theta is always between 0 and 180. If you go beyond 180, you will just add another minus sign. You can probably decipher that your own way. And as we discussed, A cross B is never equal to B cross A, unlike the scalar product or our mathematical algebra. Here a minus sign comes before one of the operators, one of the sides of the equal to sign. That shows that direction of the resulting vector will be just opposite to the vector which is formed from multiplication of A and B. And now, similar to our scalar product, where we used to get A B cos theta, and this directional sign was not there, we will have certain formula here. Since we have a value called sin theta, we know sin 0 is 0 and sin 180 is 0 and sin 90 is 1. So if two vectors are perpendicular to each other like this, then you will get the value of sin theta as 1, and hence you will get the maximum of the cross product, because sin theta has a maximum value of 1. If two vectors are parallel to each other, theta is 0, and hence the cross product vanishes. As you can see here, if A and B are parallel, you will have a result 0. Unlike in case of scalar products, where if you multiply the same vector to itself, you will get a scalar quantity that is A square. Here you will get a quantity which is 0. So it's quite easy to see the similarity and differences between cross product and dot product. There are certain rules though that you need to remember, and you remember we represent a vector like this. In scalar product also we had discussed about this. If a vector is represented as a1 I cap, this is I cap, this is j cap, this is k cap, I cap, j cap, k cap. So there are 9 terms, because this will be multiplied with all 3, this will be multiplied with all 3, and this will be multiplied with all 3. So there are 9 terms of cross product, and as you remember in scalar product 6 of them were vanishing, because when you multiply dissimilar thing, I cap with j cap or j cap with k cap, the result was 0 in case of dot product. Here the reverse is true. Here when you multiply similar vectors or the parallel vectors, you will get a 0, otherwise you will get some value. So since there are only 3 possible similarities, I cap with I cap, j cap with j cap, and k cap with k cap, you will have 6 terms in vector product. As you can see here, you will have a2b3 I cap, this is j cap, this is k cap. So there are 6 terms which can also be written as a matrix in the matrix form. This is I cap, this is j cap, and this is k cap. So I believe most of you must be knowing how the matrix determinant works. You have to start with I cap and you have to multiply these two, a2b3 minus b2a3, a2b3 minus b2a3, and then you will start with j2. You have to multiply this with this and this with this, and there is a minus sign in front of that. So first you will write this term a3b1 and then a1b3, that is j cap, and in case of k cap you will have a1b2 minus b1a2. So that is why you can write cross product in terms of determinant and it's quite easy to multiply them and find out the value. So it's quite easy. Once you know one of the vector operators, you will be able to understand how the other operator works. So it says the vector resulting from the vector product of two vectors is called an axial vector, while ordinary vectors are sometimes referred as polar vectors. Thus, in equation 11, C is a pseudo vector. Equation 11, C is a pseudo vector because it is the product of two vectors, while A and B are axial vectors. So we'll discuss about polar quantity and how the sign is changed in our subsequent classes when we'll learn curvilinear coordinate system. And now we'll try to find out one operation or one use of this vector quantity. So let's try to draw it here. Let us say I have a this is vector multi vector product, or we call it cross product very popularly. There are some other forms or other names of it, like one we learned few minutes back, which is outer product. I have never heard of it in other books, but since it's a textbook, we must believe it. So let us try to find one physical use. Let us say I have a bottle. I am showing it from the top, where this is the cap. Okay, this is the cap of the bottle, and let us say I tie a rod, metal rod from the cap, or what you do in wrench. If you have a metal wrench and you're trying to open a bolt, let us say this is a bolt. I'll redraw it. Let us say it's a hex head bolt. Sorry for the drawing. And you have a wrench here with a handle, and you're trying to open it. So if the length of this wrench is R, and if you are applying a force F, you remember force has a direction. You will be applying at this direction, then this direction, then this direction, then this direction, and it's not varying very fast like the angular momentum. So you will always have a direction of force. It's not angular force. And since this is the axis of application of force, you can give R as a vector. So in the torque wrench, we find out torque, that is represented as tau. It's a vector because with this application of force and R, the nut either comes out or it fits in. So the movement of nut is basically perpendicular to both F and R, and it depends. If you try to push it this way, you are multiplying F with R, and if you're trying to pull it this way, you're multiplying R with F. So based on this, the nut will either open or close or fit in. So it's like the direction is reversed, that is in in a way same as the vector algebra that we just learned. We say torque is always equal to R cross F. So this is equal to, in expanded form, is equal to R, that is length, F is the force, magnitude of force, sine theta is angle between R and F, and a vector quantity to make it vector, to make this vector. This is the unit vector. We generally denote it by n cap. N is the direction which is perpendicular to both R and F, and it's a unit vector, so it gives this quantity a direction. So as you remember, sine 90 degree is always 0. So that is why if you apply the force on this body at 90 degree, you will get maximum torque on this nut, and you'll be able to move it. Another thing you might have seen on the mechanics who try to open truck tire, large vehicle, heavy vehicles tire, they use a pipe on top of this stuff to make it even longer, and they apply force here. So this way they increase the radius R. This is the length now, and since they increase R, they increase this quantity, the total torque increases. So this is why they use longer torque wrenches. And if you have seen the heavier screwdrivers are generally longer than the light screwdrivers. You might have seen electronic screwdrivers, they are never very long. One of the reason is because you try to open very small components, you need very precise movement of the tip, so it has to be very small. And the second reason is you don't want to apply too many torques, too much of torque in the screw while opening or tightening it. On the other hand, if you are trying to open a bolt of say 20 millimeter diameter, then you need a larger torque wrench. If you need to open a bolt of say 40 millimeter diameter, you'll even need a longer torque, larger torque. So the torque wrench or the wrench, monkey spanner, or whatever you will be using it for opening the bolt or nut, the length will increase. That is how it works, and that is mathematically covered in vector product. So now you know why the torque wrench has its length. It's because human power or human capacity of applying force is constant, with slight variation. Means if a thin or if a muscular guy is trying to apply a force, he will certainly apply about twice the force of a lean man, but still he will not be able to apply 10 times of the force. So if we have a force that is limited, so we try to vary the R, that is the reaction length, to increase the torque. So probably that's it very much. We know how the torque works and how the mathematical we will not go into these things. These are not required in the basic classes, as I believe. And we already saw the mathematical products, and this we can probably take 15 minutes in our subsequent classes later on, and we can discuss these things when we'll be learning some implementation of these quantities, cross product and all. For now it is of no use. So in the tomorrow's class we'll see how vector triple product, scalar triple product and vector triple products work. Triple products means you are already seeing it, and how it works and what is its physical interpretation. Yeah, probably we'll see that before moving on to the next chapter or next topic. With the vector triple product and scalar triple product, probably we will have plenty of stuffs to begin with. We'll have some knowledge about the basic of vector operations, and we are not going to learn the vector differentiation and all for now, but yeah, certainly we'll learn it sometime in the future. And these things we'll try to derive these things, but not now. I'll try to keep these things simple, because I've learned that many of the beginners, the persons who are new to mathematical physics, stuck somewhere here and then they leave learning mathematical physics. So we'll try to come to this operator next time after the vector and scalar triple product, and we'll learn these things. Probably it will be handy to learn these things, and then probably some of the mathematical things and these formulae which are quite important. Then we'll go to curvilinear coordinate system. So this is our plan. So I hope you guys enjoyed today's learning, where we learned vector multiplication or vector product, and I would request you, each one of you, whoever sees my video, to put at least a small comment whether you like my video, whether you want it to be fast, you want me to go slowly, or anything, or if you have some questions you can write there. I'll try my best to answer them and check them. If I have some improvements to be done, I'll definitely do it. Okay, see you, bye bye.